Hello everyone. Let us start week 7, session 1 today. We are talking about distributed training and scaling AI systems. We'll start with parallelism fundamentals and we'll try to see how we transition ourselves from training our models and AI workloads on a single GPU to multi GPU hardware or on multiple nodes with multi GPU systems. We would do hands on at the end of all the sessions of theory in this particular week. We will be doing hands on using NVIDIA DGX H100 server. This server has 8 GPUs and all of these 8 are connected using NVLink. So let's start with the session 1 today. Let's try to understand why do we require distributed training. Okay, the idea here is to understand the math which is very difficult to fit on a single GPU system. There are three ways by which we can discuss on the requirements of distributed training. The first one is the model size. Gradually, the model sizes are increasing for the models which we are using, and the hardware required is also becoming short of the memory required. Okay, the dataset size is also increasing, and the Walcock pressure, in a sense, the time required to actually do the testing, the research, the iteration is now condensed to hours, days, and not weeks. So the idea here is to understand what do we mean by model size. Let us see this. We have for a LLM or for any model, let us say we have about 70 billion parameters. And if we assume each of these parameters is using FP16 for storing the data, we end up at about 140 GB. That is actually twice the size of H100 memory. H100 GPU has got 80 GBs of memory. Now, if I am working with a model which is actually having 70 billion parameters and which actually requires 140 GB, how is that I'm going to now use a single GPU for doing that? Whether it's possible, it's not possible. If we have multiple GPUs of H100, let us say I have 2 GPUs of H100, so I actually am able to get about 160 GBs of memory. Now, how do we use that type of a system, right? And what do we do, about the various optimization states, activation, and the weights, of course. So what are we going to do about it? The data set size also is increasing. Let us say LLM pre-trained budget for application is somewhere near to 15 T tokens. So that basically means at about 3 to 5 billion tokens per day on one GPU for a 7B model, the time required to actually do the training, is basically in years. It's not a viable timeline, right? We are talking of 3 to 5 billion tokens per day, though it's not less, but just with one GPU for a 7B model, and that basically means I'm just talking of 7 billion parameter models, right? Not 70 billion as we discussed for the model size. And then, since this is the status, the pressure and the return of investment required by the companies, is that we need to actually compress 2 weeks single GPU experiment down to basically hours across a cluster. So this is the actual need. Okay. Now we see the reasons of why or what is the problem being faced by us as well as people who work in the industry on these AI models. There are three reasons or three basic issues, right? The first is the iteration time, the second is the model size, or majority of the cases it's both, right? So to solve this specific problem, we try to understand how can we increase parallelism even though GPUs are themselves massively parallel systems. They work with huge amount of data and execute their workload parallelly. But how do we still increase, okay, the parallelism? So we can discuss that at four levels, right? Or they say four axes to parallelize. One axis is data parallelism. That basically means we can replicate the model, split it into batches, and then all gradients, right, can be collected together as a last step. So this is a way of trying to basically split your data in parallel among various GPUs, right? And then try to collect back the gradients in the end or once per step from all of the GPUs which are involved. This type of approach is generally used when the whole model fits, okay, and when we want more throughput. The second type of parallelism, or the way in which we can parallelize things further, is we can do the batch wise split, okay, and we can split the weight tensors, the columns and rows, and again we can have all reduce activations inside each layer, and we can use this when one layer does not fit, okay. For example, the model like magnetron, we can use this type of a parallelism there, okay. Pipeline parallelism basically tells we can split the layers, okay, and communication is we have this forward activation, gradients actually have the backward pass, right? So this type of parallelism again can be used when we have the model which is very deep and we actually cannot use just one GPU for it, okay. The fourth approach is to do sharding. There's a sharded approach, right? So we have fully sharded data parallel approach, and then there is zero redundancy optimizer is another approach, right? That's called a zero. So in both these cases, we will split the weights, the gradients, the optimizer states among the GPUs involved. We'll have all gather weights, reduce scatter gradients, all of that. These are actually approaches which are used in parallel programming when we talk about OpenMP, MPI, and all of these parallel communication and parallel compute techniques, right? Not going into the details of them, but the basic idea here is when we are talking of lot of memory bound applications, but we want execute speed, okay, to achieve data parallelism and execution at a faster rate. We should also remember that when we are talking of memory bound application, which is not very compute intensive, and the application is purely memory bound, the time it takes for the data to transit between various places and locations actually hides the compute speed, right? So that becomes the bottleneck. So the latency time, okay, actually sometimes hides the compute speed. So that is where the problem starts. And GPUs, as they are used for compute intensive applications because we don't want GPUs to be kept idle. Okay. So these are four ways of parallelizing your program further. Even though you have GPU, but if you have multiple GPUs, how are you going to do all of this? Right? You have to split. You have to split the model. You can split it into batches. You can split the layers. Right? You can split the weights, gradients, and optimizer states. So various ways of trying to do it. Right? Each of them have their own advantages and disadvantages, though. We can combine all of these three things again. So at present, at the frontier scale, we can combine the data, the tensor, the pipeline at once. So we can assume that each GPU, okay, basically has a PTD coordinate. That basically means pipeline, tensor, and a data coordinate. And we can actually have the dimensions multiply and we get 4 into 8 into 8, and we can split that and run it on 128 GPUs, right? So we can start with something like, we can start something with DDP, that means distributed data parallelism. We will have the memory problem, so we solve it using FSDP or 0, I told you. If there is one big layer, we can use tensor parallelism. If the model is too deep, we will use pipeline parallelism. So all at once, so what we can do is we can actually start the DDP, that means data dimension, data splitting, and then we can use tensor and we can use pipeline, right? So tensor ranks live on the same NVLink. Pipeline stages spans the nodes. Data replicas span the racks. So this basically means the complexity or the information, okay, where is it actually kept? At what level you are trying to have the communication? Depends on the topology of your distributed training hardware system, right? So we have NVLink, we have nodes, and we have racks. Okay. So at what complexity, which particular thing we are going to use is what is briefly explained in this particular slide. So now let's try to understand a bit of when we say about distributed parallelism, what are the various vocabularies or what are the various words which we will be using when we actually do the hands-on as well. So I will use that. So world size, that means total number of processes. We actually have a concept of 1 per GPU. So we assume that one particular process is running on 1 GPU. When we say we have got 2 nodes and we have got 4 GPUs, this means our world size is 8. This means one node has got 4 GPUs. So we have got 2 nodes. So we'll get 8 GPUs. And by default, let's assume we are running one process per GPU. So our world size is 8 processes. Okay. Rank 0 to world size minus 1. Unique per process across the whole job. So this means, let us say we have a job and there are total so many processes. So we'll rank each process, right? People who have done MPI will be able to understand and correlate it better. So if you're not done, you can just go through a brief idea about MPI. Okay, that's message passing interface. So 0 to world size minus 1. So world size is now 8. So our rank globally for each of these processes will start at 0, that is rank 0 process, to rank 7 process. This is all uniquely numbered. Now local rank, one is a global rank, one is a local rank, because inside GPU, right, you can bind, okay, uh, and then you can use it as a local rank thing, right? So GPUs per node, when we say, that is what is the local rank. It varies from 0 to GPUs per node. And node rank basically is 0 to n nodes minus 1, which machine, process group, the communicator. Default is all ranks. So the basic idea is we are trying to have the total number of processes. We have them named globally. Then we can give them a local rank. We can also link it to, okay, one of the nodes, and then we call it as a node rank, right? So this is how the distributed launcher, or when we start distributing our workload, okay, these are the various terminologies and vocabulary which we generally use. Now when we're going to distribute it, right, so you have got certain processes which have got their own numbers. You can communicate among processes using those ranks, okay, and then there has to be this communication backend, right, which helps us to communicate. So one of the things which I was telling was MPI. Then there are two things which we should just have a brief idea about, which we will be using also. NCCL is something which we'll be using in our hands-on. We have something called as glue, glow, and MPI, right? So this is NVIDIA Collective Communication Library, which helps us to communicate between GPU to GPU. That basically means we have this concept of communication between two GPUs, right? And if we are trying to have a DGX server, we have got NVLink, which are connecting all the GPUs, right? So we have this NVLink thing, which is intranode. So inside a node, right, we have this NVLink. And then we have this RDMA, which is internode communication, which is topology aware, right, type of a communication medium. So NCCL, when inside the, let us say, DGX server, it uses NVLink. But if there are two DGX servers, okay, we will use RDMA over IB bar ROCE between two nodes, right, and it is topology aware. So this NCCL is generally default for GPU training, and almost every time we use a NVIDIA GPU, we will be using internally NCCL. So this glue, which is this Facebook's cross-platform backend, it basically is CPU friendly, right? It does not have the concept of GPU application acceleration, basically. So when you want to debug something which has multi CPU type of stuff, you can actually use this framework, right? And in a hybrid type of environment, wherein you have got a lot of CPU clusters and a lot of GPU nodes as well, you can actually use this also to actually link your CPU GPU computation, okay. And majority of the times, like HPC people who have been working with HPC basically are more inclined to using MPI. So as I told you, message passing interface, and PyTorch supports it, but it requires a rebuild. So we would be using PyTorch in our hands-on. And we have got another thing which is called as Horoword, which uses MPI under the hood, but it requires a different type of a setup, right? So since we already have PyTorch, which is commonly used, right, and a lot of people use it, so I am showing you basically PyTorch with NCCL and MPI at the back end, right? So this is what we are going to do in our hands-on. So this is what is basically the communication thing about the distributed training part. Next, so when we try to distribute things, right, there are certain collective primitives which we generally use, which we should know. There's something called as broadcast, there's something called as reduce, there's called all reduce, there's all gather, there's reduce scatter, there's barrier, right? So these are all primitives which are generally used internally by PyTorch, right? So you'll have to broadcast, right? So when you broadcast, let us say it syncs the initial weights from rank 0 to all the ranks. So you broadcast, right? So you broadcast it from 1 to n. Reduce is when you want to take or sum up all the gradients, right? And give it to a single main ranked process, right? So there you use reduce. So people say it's old style. It's rarely used directly now, but still that concept of collecting everything and being maintained by a single process, okay, is useful, right? And then we use all reduce, wherein every information is given to all the people. So that is where the gradient sync in DDP happens. And this is the basic idea about distributed training. But you will have to also see how we optimize the memory part of it, right? So all gather also goes from end to end, reduce scatter also goes from end to end, and then barrier basically is to sync, right, various threads which are working, various processes which are executing. So all workers wait until every rank arrives before proceeding. So this is how basically it is. And this is the basic idea about how various primitives are generally used. So let's try to see the practical aspects of when each of these things basically are used in practice by the industry. So let us say you have a scenario wherein you have 7 billion fine parameters to fine tune. So there's a 7 billion parameter fine tune model. You have got 8 GPUs. So what all will you use? Let us say you will surely use data parallelism, data parallel. So you use DDP, tensor parallel not required here, pipe parallel not required, FSDP if you require certain more things. So sharded or sharding is actually used. Now if you are using 70 billion parameter pre-trained model and you are running it on one node with 8 GPUs, right? So the assumption is we are having B200 Blackwell 200 GPUs. Even if you assume that 8 into H100, right? B200 is the latest one, so there's a reason I wrote it. But if that is the case, you require tensor parallelism and you require sharded. Okay, data parallelism becomes very challenging. Pipeline parallelism also becomes challenging, but tensor parallelism at that level, right? Because you have one node with 8 GPUs, right? So that is how the thing is, and then you can use this. So 70 billion pre-trained with multi-node, you can go for data parallelism, you can go for tensor parallelism within the node, across the node you can go in for data parallelism, within the node you can go for tensor parallelism, and sharded you can go if you require. Pipeline parallelism is optional, but again for this type of this thing, right, it depends on whether you really want to use it or not, because whether you will get that efficiency. Okay, so GPT-4 class frontier model, the latest, the most complicated, the most advanced model. If you want to do so, yes, you can do everything actually. So you can do data parallelism there, you can do tensor parallelism there, you can do pipeline parallelism, you can do sharded, right? So you can use all the four combined together for achieving faster learning, faster training, right? So that the inferencing becomes faster. So there are certain things like work scenarios wherein the basic idea is to understand if the model fits on one GPU and we want 4x more throughput, what is that we are going to use? We will use data parallelism, right? We are not memory constrained, so we will use data parallelism. Model is 200 billion parameters. The biggest single layer fits on one GPU. So memory is constrained, not any one layer. Shard the weights plus grads plus OPT states, something like this. If we work on single transformer layer, okay, and we know that all the weights on that transformer does not fit on one GPU. So we go in for tensor parallelism. So we must split the weight matrix itself, not just the batch, right, and the model. And let us say we want data parallelism speed, but also need to shard optimizer state. So we can use FSDP or 02, which is the latest one, and which gives us the DDP like training loop and many memory efficient optimizer sharding techniques, right? So these are ways by which you can just understand as to what type of parallelism you can use. So here, parallelism is in the context of distributing the workload further, right? Even though GPUs are massively parallel in itself, but how do we actually consume and use more GPUs for processing huge amount of data faster, right? So this brings us to the end of session one, wherein we saw four parallelism axes. We talked about how basically these parallelism methods could be combined, right? We also saw there are three backends, right, which we can use. And we basically start with distributed data parallelism and then try to shift our focus towards tensor parallelism, pipeline parallelism, and all the types of parallelism, okay, the frontier scale thing. So this is what uh, was there for the distributed training introductory session 1. We will all meet in session 2. Thank you.